like, you know, you did it wrong because your momentum should keep going in the same direction unless you put a thrusters. Oh, you're right. And then it gave me another section of code that I just replaced the section of code, and then it worked. And I was like, well, can you make some sort of indicator that the thrusters are on? And it says, yeah, sure. And then it gave me another section of code, so when I hit the space bar, a little booster came out the back, like a little fire came out the back to show that it was going. And there was like, actually also, I don't want the rocks to be circles, I want to be more rock-like. And so it's like, sure. And then so it changed the object for the rock to like, instead of being circles, it made it like random, like jagged and stuff like that. It's cool. Well, I'm always nice to it. See, that's what we talked about. You'll always be nice to ChatGPT because when it takes over the world, it will always know that I was nice to it. I always say please and thank you. I swear to God, I absolutely do. I should. I'll do it. Yeah, it's Python, right? So you could just run the code. Okay. Okay, so I just set this thing up. I set I just set up all my variables, right? Omega bar, 0, 0, so it's omega naught in the K direction, right? Omega A relative, I guess, is 0, omega A bar, 0. And then I take those two and I add them together, right? So this is the omega of the secondary. That's the omega of the wheel as seen from the secondary, right? And then I go through and I set up my different vectors for my directions, right? And then here's my VG, is I just cross omega bar with RG as seen from C. Then to VG2, I then just cross omega A with RG as seen from D, right? And I just carry it out, and there's their answers that we had before, right? Those should all be the same answers that we get, VG2, right? And then I just kept going with it, right? And then I determine what my alpha is. I say what my VP is. I figure out what AG is, and then I figure out what AP is, right? And there's all the same answers that we got. So a little bit of work up front, but once you get this squared away, just run with it. The problem is, right, you don't have this on an example. But this is an example of where what you learned in MATLAB could be used in not the real, almost in the real world. We're still in academia. Okay. So that's it. That's kinematics, right? It's the same ideas that we had before. We just had this extra component, right? This added complexity that was associated with a thing that's rotating about multiple axes, right? A thing that's rotating about another thing that's rotating, or rotating within another thing that's rotating. But once you figure out what the body is, what the secondary is, it's all the same. It's all the same type of problem. It's all the same thing. Taking a step from one point to another point, right? They all the problems in the book fall into that same category, right? This is one of the most complicated ones they had, right? If you were to solve this one, like if I was after the acceleration, or velocity at point B, right? I know that the velocity in the very center of this thing is going to be 0, so I just take a step from here out to here. But then the omega that I use, I'm out on a body, I'm on the body, so I have to take into consideration that this is rotating, and then the thing that's rotating about is also rotating. So I'd have two components in my omega when I make that step, right? Same thing with alpha. If I was looking for the acceleration of point P, I would have to take into consideration that I'm going to have an alpha about this axis, right? In this case, about the x-axis. I'd have an alpha about the x-axis because I've got a thing that's rotating about thing that's rotating, and it's changing directions, and so there's going to be an alpha. And then so I would take a step from here, which is 0 acceleration, out to point B. When I do that, it's all the same things. And I think every problem in the book is the same way, okay? But now we get down into the interesting stuff, okay? So now all of that was just how are things moving relative to each other. Now what we have to talk about is how do those things relate to moments, right? How do those alphas relate to moments? And the forces is fine, right? Force is just mass times acceleration, but it's the moments. How do those moments, right? When you had that little fidget spinner and you rotated it around, you changed directions, you felt it wanting to turn over off axis, but you didn't let it turn over off axis, right? You held it in place. So you applied a couple right where you were touching it. You're applying a couple when you did that. Well, how big was the couple that you applied, right? Well, that's what we're on our way towards, okay? Is how does those changes in directions cause, moments and velocities, or moments and forces rather, okay? So first thing you got to do is talk about angular momentum, right? This is what we did before. We started out with angular momentum, and based off of that, we were able to then, transfer over to the moment equation. Okay, so we first talk about angular momentum, right? Angular momentum, again, is going to have two components associated with it. It's going to have the angular momentum about its own mass center and the angular momentum of the mass center about whatever point you're talking about, okay? So that's the total angular momentum, right? And then what is hg? Well, hg is this integral that we have right here. The problem now, though, when we did this before in 2D, what's really nice is that in 2D, I'll write some over here, just kind of compare it. In 2D, omega was only in the k direction, and then r was only in the x, in the I direction, in the j direction, right? And then when you carried this out, this is where we got the integral of r squared dm times omega, where this just became I. And just to refresh your memory, right? When we were in 2D, we got to this point, we restrained it to 2D, or constrained it to 2D. And when we constrained it to 2D, then, you know, r was just in the x and the y direction, and then omega was only in the k direction. When you did that constraint, it just simplified down to r squared dm, which is just what our moment of inertia times omega was. Right? This is what we used to solve that problem in the last homework, which is I times omega was the angular momentum. Okay, but now this is a problem. This is a problem because now omega isn't just in two directions, right? Omega's in three directions, right? And my r has three components to it as well, right? So if I take this and I substitute this and I end up here, and I take this and I substitute it and up here, right? This thing blows up, okay? It becomes this. So that is the angular momentum of a 3D object about its own mass center, right? When you carry that thing out. I mean, obviously it blows up. I think the book has a more thorough derivation of it. I think the most important part is you know that it blows up. It started out as something simple. It when 2D, it simplified way down. In 3D though, the thing blows up, right? And it becomes what you see right here. In vector notation, or sorry, matrix notation, this is what it looks like. These are equivalent to each other. Right, those guys are equal to each other. If you write it out in equation form, it's up above. You write it out in matrix form, it's down below. Remember how matrices work? You guys remember how matrices work? Okay. Take matrix multiplication, you take these three and then you flip them up and you multiply it by the corresponding and then you add them up, and that's your upper one. You take the next one, rotate it around, multiply it by the corresponding, add them up, and that's the next one. And so if you did that, if you wanted to, you could verify it that they're the same. You take these guys and this gets multiplied by this one gets multiplied by this one gets multiplied by this one, and then you add the three together, and then that's the number that's right there, right? And so then, and that would be, you know, what that term is right there. So that it is. So we're gonna look at it in this form, right? And actually, eventually we're gonna derive our moment equations in matrix notation as well, right? But I guess what's neat about it is it does simplify down to just I times omega, right? It is. It's just now, right now, omega is three terms, omega x, omega y, and omega z, and then I is a matrix, right? That's a tensor. We can call that a tensor. It's an inertia tensor. That's what that's called. Oh, the I is rather the I. Actually, I'm going to change. I'll fix it right there. Boom, fix it. That right there. That term right there is the inertia tensor. Okay, yeah.
Are xy and yx the same?
Yeah, we'll get into that. We'll cover that here. Okay, so you'll notice that we got this down here. We got these guys down the diagonal. We'll go red here. That guy, and this guy. Right? These are our product, or our moments of inertia. Right? Those are our moments of inertia. IXX, IYY, IZ. That's what we've been using so far. We were doing IZZs. IZZs is what we use for everything else. Right? So it's IZD that we're used to using. Now we got all these other things. These off-diagonal terms, this guy, this guy, this guy, this guy, this guy, and this guy. These are what we call products of inertia. It's a new concept. We haven't talked about products of inertia yet. Right? And then we'll also mention that it is symmetric. What does it mean to be symmetric? It just means it's mirrored about the diagonal. So that answers your question before. Is IYX the same as IXY? And yes, right? It is. It's how one affects the other, and then if the other should affect the same one the same way, right? It's a relationship between the two. Okay. So then how do you calculate this, and what do they mean? Okay. My notes are all messed up here. Okay. Let me make sure I have enough room. These guys are products, these are moments of inertia. This is the body's resistance to rotation about axis. Right? Same definition we had before. A moment of inertia is the body's resistance to rotation about an axis. Right? So you're going to have, depending on which axis you're looking at, you're going to have different moments of inertia. Right? That's the moment of resistance about that. These guys over here are my products of inertia. Right? It is a measure of imbalance or asymmetry. In an object. This can be positive or negative. Right, the actual value. When it goes in there, it's the negative of the actual value, but they can be positive or negative. And what they do, since they're on the off diagonal, is they couple motion about one axis with momentum about another. We'll spend more time with these next time. We're running out of time here, but it's a measure of imbalance, right? So something that has perfect symmetry, it's not going to have any products of inertia because it's symmetric about all the different axes. Or if it has, we'll talk about symmetry in a minute. But if there's symmetry present, you don't have products of inertia. If you have something that's imbalanced to something that doesn't have symmetry, then you're going to pick up a product of inertia. And if you look to see what they're doing, right? This top term right here. This top term, if I do my matrix multiplication, right? I take this times this plus this times this plus this times this, right? And then what I calculate, this upper term would be the momentum about the x-axis. And you can see if I have products of inertia, my momentum about the x-axis is going to be affected by what omega y and omega z is. So y would be rotating about one axis, be causing momentum about another axis. Well, that happens with something that's imbalanced, right? And so a perfect example of that is if you've ever driven in a car with imbalanced wheels, right? If you have unbalanced wheels on your car or unbalanced tires, right? Then you pick up like a shimmy, right? So what they're balancing is they're balancing rotations about your axle, right? If that's not balanced right, it's imbalanced in this direction, it picks up, it makes it wiggle in the other direction, which is just really weird. And so everybody's felt that before. Driving down the road and then your car's like, your steering wheel's going like this as you're driving, and you're like, how is that happening? Well, it's happening because of you have a product of inertia because it's not symmetric, okay? Anyways, we'll dive into this a little bit more. And where we're headed, good news is most of these terms, we don't actually have to carry out these integrals. Most of these terms you'll find in the book, right? But what we're headed towards is this. That's our moment equation. Right? 3 of them. 3 moment equations. Good times.